Hi, so this is module 3, lecture 3. So here are the resources again, right? I've got code here. This code, right? This data is actually in R built in. It's in this package, library ML bench, that we'll install, work on together. So you don't necessarily need to download anything for this, but I would definitely encourage you to walk through all this code at the end. I may have this on the slides, but I just kind of want to show you about libraries. So, and kind of explain what it is. So basically in R, what you can do and what a lot of people do is they'll make R packages that you can actually upload into R and use. So for example, one of my functions that has been used a bunch is this subtype package, cran. Is this subtype package. So this has been used to conduct clinical trials at Dana-Farber for dose finding in pediatric cancer patients. And I have like a whole bunch of different functions in here that you can use. It's got like a help menu. These are all the functions. You can go to it. Here I have, what actually the function does. This is the argument. So this looks a lot like, right, the help for t.tests. So, the help that you'd see, help t.tests. And you get this help menu. It provides those kind of things. So we can actually load my package into R if we wanted to by doing two things. The first thing you're going to do is you're going to go to install packages. And I can come here and type in subtype. And it should look it up. So this is going to download it from the internet. So it's downloading, tells you, where it's going to be. And it says successfully downloaded. And then if I actually want to use the package itself, I can type in library subtype. So you only have to install it once, but every time you actually open a new R session, you have to use this library command. And more or less what that command is telling R to do is, hey, look, I know you installed this package already, go find it and load it into R. So I load this package and now I can actually use the function, get ESS. So it wasn't there before, now it's there. So that is here. The reason I'm telling you this is the code that we have here is going to use the ML bench package. So you're actually going to have to install it. So again, just show you how you do it again before we move along. You're going to go to tools at the top, install packages. I'm going to type in ML bench. This is going to install the package. It's installing the package. And then now that I have it, I'm going to actually have to type in library ML bench. And then it can run. If you do this for a package you don't have downloaded, it'll give you a problem. It'll say something like, I don't know, library. I can type in like M1. It'll say like there's no package. And so it would have said that for ML bench if I didn't install it already. So I have to install it first. All right. So the lecture material is here, PowerPoint 3. And let's go through it. So this is 2 sample tests for categorical variables. So here, let's think about 2 different categorical variables. One could be xi, which is whether or not it rains today. It could equal no rain or rain, or it could be a 1 for rain and a 0 for rain. And then let ti equals whether it rains tomorrow. So ti could equal no rain or rain. Also, ti could be a 1 for rain and a 0 for no rain. For categorical variables, we can compare the proportion of tomorrow's rain in the 2 rain groups today. So basically we can look at, okay, over time, maybe throughout the year, I'm going to observe, does it rain today? Yes or no? And does it rain tomorrow? Yes or no? At the end of the year, right, I'll have a whole bunch of times, I'll have data that says, does it rain today? Yes or no? Does it rain tomorrow? Yes or no? And maybe I want to know, is the % chance that it rains tomorrow different given that it rains today versus doesn't today? So I can do that. I can also compare, test whether rain tomorrow is independent of today. So the first way, if I want to test that these 2 proportions are equal, I'm going to use a 2 sample test of proportion. So here, let pi 0 denote the probability of rain tomorrow given no rain today, and let pi 1 denote the probability of rain tomorrow given rain today. So right, what's happening tomorrow? So my null hypothesis is that these 2 proportions are equal versus my alternative, they're not equal, i.e. the probability of rain tomorrow is the same whether or not it rains today. This is also testing for independence. Why? Because pi 0 is equal to the probability that ti equals 1 conditional on xi equals 0. And pi1 is the probability that ti equals 1, conditional on xi equals 1. So conditional on it rains today. So here's another example. This is from a book by Alan Agresti from the 90s. And this is looking at self-identified gender and whether or not someone believes in the afterlife. So this is your first sort of look at what a contingency table looks like. We have kind of looked at these in R a little bit, but the way to read this contingency table is I have a column here for gender, male and female. And so in each row, in this first row, this is going to be the number of females who responded yes and no or undecided. So 509 self-identified females in my data set said yes that they believe in afterlife, compared to 116 females that said no or undecided about believing in the afterlife. Similarly, 398 males here said yes, they believe in afterlife, and 104 males said that they're no or undecided. So if I want to get the total number of males, it'd be 398 plus 104. If I want to get the total number of self-identified females in my data set, it'd be 509 plus 116. If I want to get the total number of people who do believe in the afterlife, it'd be 509 plus 398. And if I want to get the total number of people who don't believe in the afterlife or undecided, it'd be 116 plus 104. So in general contingency tables, let's suppose there's some factor with X levels and another factor Y, or some factor X with M levels. So it's a variable. In this case, could be gender, and it has 2 levels here for this self-identification, just as the data was collected. And another factor Y, which could be yes, no, do you believe in afterlife, with K levels. Here, K is 2. Then the way we'll define these is R1 to RM. These are the level values for each factor, and C1 to CK, these are the level values for the columns. So I've got the row factors and the column factors, what values each variable could take. So in the rain example, R1 equals C1 equals rain, and R2 equals C2 equals no rain. So right in that other example, you know, I can have, hey, look, I've got this here. Did it rain on day 1? You know, day one, I can say no, yes. Here is day 2 over on this side, and I can say no and yes. So the counts that I'll see here in the data set, that's going to be the number of times that it didn't rain today, but it did tomorrow. This is going to be the number of times it rained both days. This is going to be the number of times it didn't rain either day. And this is going to be the number of times where it rained today, but not tomorrow. So here, right, I'm just doing some notation, just kind of expressing what it is. Nij, this is the count in the box corresponding to factor level I of factor X and level J of factor Y. So in this example here, N11 is 509, N12 is 116, N21, the second row, first column is 398, and N22 is 104. Then N1 plus I plus, this is the sum of the counts in a row. So this would be, in that example, total number of males or females. N plus J is the total number of counts in each column. So this would be the total number of yeses or no or undecideds. And then N here is going to be the sum of all counts in the contingency table. So just looking at this, right here, we have it all spelled out. This is just sort of the notation you use when talking about contingency tables like this. I have N11, that's 509. I have N12, that's 116. I have N21, that's 398. I have N22, that's 104. N1 plus is the total number of females, that's 625. N2 plus is the total number of males, that's 502. N plus 1 is the total number of people who believe in the afterlife, that's 907. N plus 2 is the total number of people that say no or undecided. In terms of belief in the afterlife, that's 220. And then N is my overall sample size. It's the total sum within the inside of this table, and that's 1127. So again, we're going to come back to something we talked about in the first lecture, which is joint probabilities, conditional probabilities, and marginal probabilities. Here, pi1j, this is the probability of observing an x equals I and a y equals j. So in this example, right, pi11, this would be the probability if I go out and sample people that they identify as female and they, they have a belief in the afterlife. Marginal distributions here, pi1 plus, this would be the probability of each row factor here. This is probability of X, the first row of X. So this could be the probability that I sample somebody who identifies as a female versus a male, assuming, right, that those are my inclusion criteria. They have to identify as one or the other in the way that I collected the data. Or pi plus 1, this could be the probability of saying, yes, you do believe in the afterlife versus no or undecided. Here, pi 1 plus is equal to pi 1 1 plus pi 1 2, and pi plus 1 is equal to pi 1 1 plus pi 2 1. It's just like the counts here. Adding up the counts, I add up the probabilities in the same way. All these probabilities need a sum to 1. All of these probabilities too need a sum to 1. All these probabilities, there's a marginal, need a sum to 1. Then I also might want a conditional distribution. So P of X1 equals 1, conditional on Y equals 1. I can do it like this. This is the formula here to get it. And it's estimated here as P11 over P1 plus. So, or this count here. So if I wanted to estimate, hey, conditional on a self-identified female, what's the probability they believe in afterlife? It'd be this 509 divided by this 625 count. Okay, here's the estimates. Belief equals yes, conditional on female. That's this 509 divided by 625. So basically you just ignore the second row here. Overall belief equals yes probability is the total number of people who said yes, which is 907, divided by the total sample size, which is 1127. And this is a joint probability. The probability that belief equals yes and a person identifies as female in this sample is 509 because there's 509 people that answered yes to those two questions. And there's 1,127 patients total. So it's 509 divided by 1127, that's about 45%. Sensitivity and specificity are things that you might hear about from time to time in literature for diagnostic tests. So maybe, you know, you get a lab value and that lab value could be like albumin, could be predictive of whether this patient is going to have complications after surgery. So maybe you want to predict, yes, they are going to have complications and either not operate on them or take extra precautions. So think about it from this setting. Consider a diagnostic test where patients are diagnosed with a disease, X equals 1, otherwise X equals 2. If the patient actually has the disease, we can denote Y equals 1 and Y equals 2 otherwise. So sensitivity here is the probability that Y equals 1 conditional on X equals 1. That means if I say the person has the disease, my test does, what's the probability they actually have the disease? So more or less, what is sort of the true positive rate? Sensitive specificity is the opposite. It's saying, hey, conditional on my test says they don't have the disease. What's the probability they actually don't have the disease? So that's the true negative rate. So as an example, the higher the sensitivity and specificity, the better the test. So for an example, in literature, right, mammogram sensitivities to predicting breast cancer is about 86% and specificity is about 88%. So said differently, if you go get a mammogram and it says that you have breast cancer, 86% of the time you actually will have breast cancer. And if you go get a mammogram and it says you don't have breast cancer, 88% of the time it'll say you don't have breast cancer. Okay, so this is the Pima Indians data. And here I want to predict diabetes in a society of Pima Indians. I'm going to use this library command. These are people that are from India here. Library command again, and I'm going to use data Pima Indians reads in the data set. So here I've got library ML bench. Again, I showed you how to do that. You install your package and then you can use library. I say data Pima Indians diabetes. I'm saying my names of my data, names of my data. I have pregnant, glucose, blood pressure, triceps, insulin, mass, pedigree, age, and diabetes. If I look at the header here, I can see pregnant. Looks like this is number of pregnancies, 6, 1, 8, etc. Glucose, this is their glucose level, which is related to diabetes, right? Pressure, this is probably their blood pressure. Triceps, I'm not sure what this is, but some number. Insulin is their insulin levels. Mass is probably their BMI here. Pedigree, I'm not sure what pedigree is here. It's just another number. I have age, and then I have diabetes, positive or negative status. So when you actually use this data command, you actually get a data set that is named Pima Indians diabetes. But I'm just, because I'm old fashioned, I guess, I'm just going to rename it as data. equals data. I think it is consistent to name your data the same thing across different data sets. That way you can reuse your code and adjust things. It'll save you a lot of time in the future. So the table command here is good for categorical variables. So maybe first I want to look at table data diabetes. I have 268 positive, 500 negative mothers here with diabetes. Maybe I want to look at number of pregnancies. I could say data pregnant. I've got 111 people that did not have any pregnancies, 135 that had one, et cetera, et cetera. I actually have one that had 17 pregnancies. Here I can make a contingency table also using the table command. When I'm making a contingency table, I need to put my row factor in the first argument and my column factor in the second argument. So here I'm saying, hey, look, I want to create a logical variable, which is going to tell me, yes, it's going to be a true if they had more than one, if they had one child or more, or one pregnancy or more, and it's going to be false otherwise. And then I want my diabetes status. So you can see this is my contingency table here. So I just want to read through it. So there's 73 people here that had no pregnancy and had a negative diabetes status. There are 38 people that had no pregnancies and had a diabetes status. This here is saying there's 427 people that had a pregnancy and no diabetes, so a negative diabetes test, and 230 that had a pregnancy and had a positive diabetes test. So here I can define it to as something else if I want, X equals table, and then X here. If I want to get joint probabilities, the way I do that is I take X and I divide by the sum of X. So you can see that here, 9% of my sample about had no kids and did not have diabetes. 55% had children or pregnancies and no diabetes. About 30% had pregnancies and diabetes, and about 5% did not have pregnancy and also had diabetes. I can also use this command here, apply, to get sort of row probabilities or column probabilities. Actually, prop.table is going to be a little easier, and I'll show you how to use that at the end of this. So actually I can show you now. So this is a contingency table here that I'm dividing by. I'm applying this function to each row. I'm applying the sum. So what this function is doing is it's adding up 73 plus 38. It's adding up 427 plus 30, and then it's dividing the rows by each of those. So I can see here, right, 34 conditional on no kids, about 34% of people had diabetes, compared to conditional on they did have kids, about 35% had diabetes. Let me actually go to R and just show you the prop.table command, which you can also use, that I think is useful. So if I come to the code here, I'll just take my code and I'll come all the way down to right here. And I can run this now. This should just run fine without anything. I come down here, I run this. Here's my conditional probabilities at the bottom. An easier way to do this is using the prop.table command. So I can say prop.table X, and then I put in my margin. So 1 is for rows. So this is going to be the conditional probability within each row. You can see that here. It's the same thing as before. And if I do 2, it'll be within each column. So this will be conditional on somebody having a negative test. There's about an 85% chance that they had children, compared to they had a positive test. It's also about an 85% chance. Okay. So I can do the same thing here as well. So this is looking at 2 plus pregnancies versus 0 to 1. Okay, in this case, right, conditional on they had 2 or more pregnancies, there was a 38% chance that they had positive diabetes, compared to 27%. So it does look like mothers that had more than 1 pregnancy are more likely to have diabetes than those that had 1 or fewer pregnancies, 27%. So I might want to test, are these 2 proportions equal? So let's say we want to test whether women with any pregnancies have a higher rate of diabetes than women without a pregnancy. So let pi 0 denote the probability of diabetes with no pregnancies, and let pi 1 denote the probability of diabetes with pregnancy history. So maybe I want to test, this would be a one-sided alternative, pi 0 which is the probability of diabetes being bigger than that same probability for those with pregnancies, versus the alternative where it's less than. So if I reject the null in favor of the alternative, what does that say? That says pi1 is bigger than pi0, which means that the probability of having diabetes conditional that you have a child is higher than it would be if you didn't have a child. So I can do this with prop.test, but I just want to show you the formula. Here, P0 and P1 are the sample proportions in the diabetic patients and the non-diabetic patient pregnancy groups. So just as looking at the numbers, right, the P0 would be 30.34, P1 would be 0.35. Okay, and then I've got P here. This is just a combined probability. So this is just overall, ignoring pregnancy status. What is the diabetic proportion? And N1 is the sample size in the diabetic group, N2 is the sample size, or no, the sample size in those that had kids, and N2 is those that didn't have kids. This test statistic Z here follows a normal distribution if the null hypothesis is true. And you can also get confidence intervals for this difference. So it's a lot like the confidence intervals we got for mu2 minus mu1. We can do the same thing for these probabilities. So prop.test, this is how I'm going to use it. X is going to be a vector of counts of successes. So and N is going to be the overall sample size. So X here is going to be a vector containing the number of people that conditional that they had pregnancy history, the number of diabetic, and then also conditional they didn't have pregnancy, the number of diabetic. And then N here is going to be the number of people that had a pregnancy and the number of people that didn't have a pregnancy. I can adjust my alternatives in the same way. I can give a confidence interval. So let's look at this. I can actually do this. I'm going to create two vectors, Y preg. These are going to be the diabetic status of those that had a pregnancy. So I'm indexing this vector by, yes, they had some kind of pregnancy here. So number of pregnancies is bigger than 0. And then I'm saying equals equals positive to basically turn Y preg into a 1 and a 0 value. So it's a vector with 1s and 0s. Y not preg is the same kind of thing. It's diabetes status of data pregnant equals 0. So this is all the people that had no pregnancies. And I'm saying it's this whole thing is equal positive, which is going to turn it into a true false vector. How do I know it's trues and falses? I can actually take the mean of these now. So mean of Y preg, it's about 0.35, which is the same thing we saw before. Mean of Y not preg is 0.342. If I go help prop.test, it'll tell me, on this slide, I can look at what to do. And I can say prop.test, this is my vector. This is the sum of the pregnancy diabetic patients. This is some of the no pregnancy diabetic patients. And then I have to plug in my N, which is my sample size in each group. My N is just the length of these two vectors. And then I'm going to do alternative equals greater here. Now notice I have a p-value that's 0.47, which means I don't reject the null hypothesis that, these things, that the first group is bigger than the second group, first group proportion. So I failed to reject this null hypothesis in favor of this one. And you can actually look here, it gives you the sample estimates at the bottom. You can see the two proportions are really close to each other. I also get a 95% confidence interval. This is a one-sided confidence interval. You'll notice, right, it's not capped off by infinity. Instead, it's capped off by 1. And that's because probabilities, right, can only be between 0 and 1. And so differences in two probabilities can only be between -1 and 1. So the upper bound here is 1 instead of infinity. I can use prop.test to get a two-sided confidence interval too here for this. I'll do alternative equals 2 dot-sided. And you can see that here, 0.09, 0.10. Okay, this is my proportion. This contains 0. So this also means anytime you have a confidence interval that overlaps any number inside that confidence interval, you would not get a significant p-value if you tested equality to that. Confidence intervals and p-values, they're totally interchangeable. Similarly, if you reject the null hypothesis at the 0.05 level, your 95% confidence interval will not contain that value you're testing. So in this case, it's 0. I can also test whether this difference is equal to some delta by adding mu is equal to delta here, just like t-test and Wilcox test. What about multiple pregnancies? and versus 0 to 1. So here, if you have 2 or more pregnancies, are you going to be more likely to have diabetes than if you have 0 to 1 pregnancies? So here, let pi m and pi o denote these population probabilities for being diabetic for multiple pregnancies versus those with 1 or no pregnancies. I want to test the null hypothesis, pi m equals pi o versus the alternative, pi m not equal to pi o. This is a two-sided hypothesis test. So how do I do this? I'm going to do basically the same thing I did before. I'm going to get a new vector y preg, a new vector y not preg. This is going to be ones and zeros because I'm taking the data diabetes and I'm saying, is it equal to this positive value? That converts it into ones and zeros. Data pregnant bigger than 1. This is going to subset out the data there. What are the proportions here? Mean y not preg, or y preg is about 0.358. Mean y not preg is 0.272. So there is a visible difference here, but is it significant? Well, I can plug this in the same way. This is the same code that I had before, right? In the first vector, so C opens up a vector. I think we talked through that. The first vector here is going to be y preg, the sum of y preg, and the sum of y not preg. And the second vector is going to be the lengths of these two. And I can see my p-value here is 0.002, which means I reject the null that these two proportions are equal, and I consider them not equal. So here is a 95% confidence interval for this difference too. So this is the confidence interval for the proportion difference between the first group and the second group. It's between 0.04 and 0.18. So you could say, you know, we think that the probability of having diabetes with 2 or more pregnancies is about 4 to 18% higher than if you had no pregnancies or 1 pregnancy. P-value is really small, right? So you might also be interested in things like, and let me make sure everybody's with me on this, because I may have mentioned it before. If I want to create a vector in R that has 3 things, 3 2s or 2 3s, I do like this. I just put C and I put whatever I want in it, tiger, lion, bear, like that, tiger, lion, bear. It would create that vector, and then I can index it. I think we talked about how to index things. This would be the second entry, the third entry. I can also set this thing equal to X if I want. And then I can say, hey, look, print out X, get the first entry of X, get the second entry of X, get the third entry of X, get, you know, multiple entries of X, however I want to do it. So let's see, can I go back to this slide? Some other things you might be interested in are relative risk. So relative risk is just the 2 probabilities divided by each other instead of a difference. So for the diabetes example here, it'd be 0.385 over 0.272. That's a 1.42. That says, right, usually says that, interpreted, is that the risk of having diabetes conditional on 2 or more pregnancies is 1.2 times higher than the risk conditional on 0 or 1 pregnancy. And the confidence interval for this is kind of complicated, so people usually use odds ratios. The odds here, odds of success, would be pi over 1 minus pi. It's not really like odds in terms of like betting, at least from American sports books. For you know, for European sports books and things like that, it's the same kind of thing. So for example here, and then you can get the probability from this transformation here. So when odds is equal to 4, that means the probability of success is 4 times higher than failure. When odds is equal to 1/4, that means the probability of failure is 4 times higher than success. Should say success here. The reason we usually do this is people will create odds ratios, which is the ratio in the example we're talking about of the odds of diabetes conditional on pregnancy status, conditional on pregnancy history, versus the odds of diabetes conditional on no pregnancy history. So people will create this odds ratio. We'll revisit this again when we talk about logistic regression. But the reason that people use odds ratios instead of risk ratios is it's just better, easier to get confidence intervals, and it kind of matches up with logistic regression, which is the most common method, regression method that people use for categorical data. Here's the sample odds ratio. You can actually calculate this by taking a contingency table, right? So I have my contingency table that looks like this. And if I multiply this these two here, and I divide by these two here, that gives me my odds ratio. Don't worry about the math, but it does come out to be the same because these are the proportions here. So it's this N11, which is that top left column, times N22, which is that bottom right cell, divided by N12 times N21, which is that sort of off diagonal cell. So the odds ratio here for multiple versus 0 to 1 pregnancies, I can either use the proportion or I can plug in the actual counts and get that. So I get 1.67 here. And there's a hat here, so you might see some hats in statistics. We'll talk about some hats later with the regressions. So a hat is an estimate, right? So if I want to estimate, for example, if I want to get mu hat, and mu is defined as the mean BMI for males in Louisiana, I'll just go out and get a sample of a bunch of Louisiana males, calculate the average BMI, and that will be my mu hat. Okay, so anytime I get a new data set, mu hat will change. I'm trying to estimate something in the population. I can get a confidence interval for my odds ratio through this formula here. It's the log of my odds ratio plus or minus Z alpha over 2. This will be 1.96 traditionally. This comes from a Z table plus times SE. And SE here is just the square root of 1 divided by each of the count, all added up. And after I get a confidence interval, this gives me a confidence interval for log of theta. Once I get this confidence interval, I can get a confidence interval for theta by just exponentiating it. Now in statistics, I just want to point this out, log is always the natural log, ln. So from here on out, that, and in R, if you type in log, that's the default. Okay, independence. 2 categorical variables are independent if the probability of being in each cell here, each cell is the product of the probability of being in the row times the probability of being in that column for each cell. That's also, it means that theta, which is the odds ratio, is equal to 1. So here I have X, this is my contingency table based on whether somebody had more than 1 kid and diabetes here. If I want to get the odds ratio, right, I can index the two values here, X11, X22, divided by X12 times X21. You can see that here. This is the odds ratio. Here is 1.67. I can also get the standard error. It's just the square root of the sum of 1 over X. Then I can get a lower confidence interval, log of OR minus 1.96 times SE, an upper confidence interval, log of OR plus 1.96 times SE. This is my confidence interval for my log odds ratio, and then I can exponentiate this as well. So what does this say? This says that the odds of diabetes is 1.67 times more likely for mothers with multiple children compared to 1 or fewer, and my 95% confidence interval is 1.2 to 2.33. Also, again, right, this test, I'm testing whether the odds ratio equals 1. I'm also testing independence. Here, my confidence interval for my odds ratio does not contain 1, which means that I would reject that null hypothesis. Okay, chi-squared test of independence. If the rows and columns are independent, then all of the probabilities or all the counts in each row, what I expect, I can get from this formula here, which would be down at the bottom. So mu ij is the expected counts under the null. Here that I can get the probabilities in each cell from the row probabilities times the column probabilities. So I can get the expected counts if the data was independent from multiplying the row count times the column count over n. And then Nij, these are our actual observed counts. My test statistic is just going to be the sum of the squared difference between Nij's and mu Iga hats squared over the mu Ij hat. When the null is true, i.e. X and Y are independent, then this test statistic has a chi-squared distribution with I minus 1 times J minus 1 degrees of freedom, where I is the number of rows, J is the number of columns. So how do I do this in R? It's actually really, really easy. And this is all you need to do in R. I need to create my table. This is my contingency table X. And then I just need to plug it in, chi-squared dot test X here. This gives me my chi-squared test. My p-value is very, very small, which means I reject the null that my pregnancy history and diabetes status are independent. So there is some dependency there. So, and you can see before, right, that the dependency is, you know, if you have multiple pregnancies, you have a higher risk of having diabetes than just 0 or 1. Fisher exact test is the same syntax. This is also used for testing independence. These things are good, better in smaller sample sizes when the contingency table cells are small. I can use Fisher.test here. I also get a significant p-value. You can see that. The nice thing about Fisher tests as well is you're going to get confidence intervals for the odds ratios. So I get a 95% confidence interval for the odds ratio of 1.18 to 2.36. And again, I reject the null here because the p-value is quite small. With Fisher tests, I can also do a one-sided hypothesis about odds ratios. So here I'm saying Fisher test, plug in my contingency table, and I say the alternative is greater, which is saying, hey, look, the odds ratio is bigger than 1. And you can see it is, right? It's a significant p-value. So I reject the null and conclude that the odds ratio is bigger than 1, which what does that mean? That means the odds of pregnancy, and hence the probability of pregnancy, is higher for people that have more than 1 pregnancy compared to 0 or 1. So that's the end of this chapter. I want to kind of look at the homework together and just give you an idea of what I'm expecting. So let's go to the main page. Here's my module assignment. I have assignment 3. Okay, so this is assignment 3, module 3. Consider the file on Moodle. It's mdsc1.csv. I'll show you where that is. That's actually in module 2. So if I go down to, not module 2, it's in module 3, lecture 2. If I go to module 3 resources, and I go to lecture 2 resources, I have the data right here. Lecture 2 MDSC data, it's for homework. You can just kind of look at it real quick. It's going to download. I don't want that. Okay, sorry. That's not it. I need to upload this data. I will after this class. Let me just show you what it is here on my sort of on my own computer here. If I'm in module 3, this is my MDSC1 data. So I'm going to load this up so you can actually get to it. So what does this data look like? I have patient ID. I have MDSC levels here. This is a MDSC is an inflammatory marker that's in your system. There's some research that suggests it's related to COVID severity. It's definitely related to BMI. People with higher BMIs tend to have more inflammation. And this is a second MDSC score. So this is their first MDSC value and their second MDSC value. This is the race of the patient. So they're either African-American or non-African-American. This is the data, the age of each patient. And this is the treatment. Whether or not they got a treatment would be a 1, otherwise it would be a 0. So this is the data set. I have 200 patient records. I have their age, race, whether or not they received an arginase supplement, that's the treatment, and their GMDSC levels from 1 month ago, that's pre, and today, post. And again, GMDSC, it's an inflammatory biomarker, which might be related to obesity and other diseases. So I want you to do the following. The first thing I want you to do is plot a histogram of the pre and post differences. So what's that going to require to do? You're going to have to take the 2 columns of data, create a new column, which is the differences, and then you'll plot a histogram. You're going to want to use a lot of breaks here. Comment on what you see. Is the difference mostly bigger than 0? Is the difference mostly less than 0? Is the difference symmetric? What does that look like? Next, you're going to perform a paired t-test to determine if GMDSC's levels decrease by more than 5 for all patients. So for this, right, you're going to want to use in your t-test function, t.test, you want to know if it decreased, right? So here your alternative is going to be less, and mu here is going to be 5. Those are what you're going to have to plug in. Perform a Wilcoxon rank sign rank test to determine if GMDSC's levels differed in the pre and post periods. So were they the same? That's your null versus alternative, they're just not equal. Do a box plot of the GMDSE differences by treatment. So you'll do, right, how do you do a box plot? Box plot, you have a formula here. So you'll have a formula Y by some kind of true false or 1 0, 1 0 or true false. You're going to do it by treatment. You're going to do it by age being bigger than 50. How do you do that here? You're going to plug in a parentheses here. You're going to plug in data age bigger than 50. That turns it into a vector of trues and falses that you can use. You'll also use race. So does race different? Comment on the label the plots. So label the x-axis, label the y-axis, label the title, and comment on it. And then I want you to pool 3 unpooled 2 sample tests to determine if each of these factors affect GMDSE differences. So again, that's the difference between GMDSE at time 1 and time 2. So do it 2 sample t-tests by treatment, do it by race, and do it by this age group here. You can use the formula, the tilde, or you can separate out the vectors. Either way is fine. I think the tilde is probably easier. Do these results differ from the Wilcox and rank sum tests? So if instead of doing t-tests, 2 sample t-tests, if you did 2 sample Wilcox and rank sum tests, are those results different? That's problem 6. Problem 7 is, what is a 95% confidence interval for the difference between MDSC changes between arginine and placebo groups? So that's based on treatment. That's using the t-test, and you're going to want to ask for a pooled confidence variance here. So pooled equals true, equal var equals true. What about the median difference? So if I'm asking for a confidence interval for a median difference, you're going to use a Wilcox dot test, and you are going to say not equal. Okay, the next question is, determine whether being older than or less than 50 years old is independent of racial status in this data set using a chi-squared test of independence. If no, if they're not independent, so if you reject the null, tell me which age group has a higher proportion of African-American patients, over 50 or less than 50. And the last question is, determine whether treatment status is independent of race using a Fisher exact test. If not, which group has a higher proportion of treatment? So this might identify racial disparities in care. Based on all these analyses, what in your opinion is going on between treatment, race, age, and GMDSC changes? So I just want you to collectively, after walking through all of this, talk about the associations between some of these variables I had you look at. Are patients with certain race, do they have higher GMDSC changes? If they had a treatment, do they have higher GMDSC changes? Depending on their age, do they have higher GMDSC changes? And then what other factors are related? So that's the homework for today. Also, I want to point out, I'm going to add a resource here. I'll show you what it looks like. This is going to be a statistical programming resource that I've used a couple times. It's kind of a nice intro thing to R. So I have this PowerPoint, and it's just kind of some intro in R. I probably suggest kind of just walking through some of these. You can see some printouts. It could be helpful here. You don't really need to use some of these like logical statements. We're not going to be doing that here, but it could be worthwhile looking through this, getting an idea of how to index things a little bit better. All right, and I'll add that to this module. Okay, well, I hope you have a good rest of your week. And if you have any questions, please feel free to email me. This homework, right, is going to be due. I think I have the due date on it. Let me just see what it is. The due date here. The due date on this assignment is going to be Sunday, June 19th. And I'll give you till midnight to do it. All right.